Beneath the Milky Way's dusty veil lies a restless heart. Radio whispers, infrared orbits, magnetic lattices, and flickering X-rays reveal a supermassive black hole shaping stars, gas and light. Join us as we follow matter spiraling inward, decode flares without a clock, and watch gravity bend space into a luminous ring of truth. The galaxy takes shape as a disk, broad as thought, a central bar lightly traced, and long arms that curl like slow rivers. It sits in darkness like a lantern behind gauze, its clusters and nebulae and dust lanes glowing, smouldering, vanishing as the viewpoint changes. From the sun's suburb, the gaze inward meets a heavy veil, grains of interstellar dust that turn bold starlight to a rusty wash and hide the heart. So the center is not a picture, but an investigation, a patient unweaving of signals. Early radio surveys hear a hiss that the human ear cannot catch, and the hiss maps into structure, arc upon arc, a crowded bulge, an insistent voice near the middle that survives interference and time. Long wavelengths first make the unseen tangible. They pass the dust without much loss and sketch an inner brightness that exceeds ordinary clusters, as if an ember glows under coal. Over years, the maps sharpen as antennas link across deserts and plains into one extended ear, and the bright spot resolves from rumor into a durable presence. It is not alone. Around it the bulge bristles with stars, and the bulge itself sits inside a ring where gas piles up a few thousand light-years from the core, a sort of traffic circle that pauses inflow before sending it onward. The ring feeds the bar angles toward the center, and the center gathers the consequence. When infrared eyes open, the darkness thins. Space telescopes launched by the National Aeronautics and Space Administration and the European Space Agency slip between grains and pull whole populations from the night, turning the central haze into a crowded city. The bulge is not round, but a peanut-shaped swell lifted by the patterned speed of the bar. Along the ring, nursery after nursery of hot young stars throws blue light that the dust softens into red ember. Farther in the star crowd thickens until the mind loses scale. A patch the size of a fingernail on a photograph overflows with suns, and the idea of solitude fails. Here gravity is not a single pull, but a field of negotiations, a constant reshaping of orbits by near passes, tides and wakes. The closer the gaze moves, the stranger the texture. Cold molecular clouds drift beside hot ionized streams, each claiming space only a few light years from the other. Mazer's natural lasers, working in microwave light, sparkle in dense clumps as if they were beacons on a foggy harbor. Long thread-like radio filaments cross the inner region, almost upright against the disk, too straight and too coherent to be random, hinting at magnetic fields that hold their lines across astonishing distances. In places, those fields pinch and release, turning stored tension into heat and acceleration. The total impression is of a city with scaffolding, both seen and unseen gravity marking the avenue's magnetism, carving the alleys, shock fronts, painting the curbs with emission. Amid this crowded theatre, a single compact source becomes the steady point. It sits at the dynamic center, not drifting, not splitting, and its radio voice persists through seasons and solar cycles. Infrared and X-ray instruments catch brief flares, minutes to hours long, as if knots of gas tumble inward to brush a sharper edge of gravity. The light from ordinary stars cannot explain this behavior, and the statistics of many small sources fail as well, so attention turns from the light to the motions near it. There are stars in the inner parsec that move so quickly that their orbits can be traced within a human lifetime. They sweep around a focus that is not visible in ordinary light, and their paths followed year by year write a sum that grows hard to deny. When a star returns to its starting line after sweeping a tight ellipse, the time it takes and the way its speed peaks reveal the mass within the orbit. Those orbits point to something heavy and small, a concentration that no cluster of ordinary matter can hold without showing a surface, a temperature, a spectrum that should shout. Instead, the center whispers bright in radio, intermittent in higher energies, and cool by the standards of the brightest galactic cores. This faintness is its own invitation. If gas streams inward along the bar and the ring as maps suggest, why is the glow so modest most of the time? If the central engine is massive enough to sculpt those tight orbits, what restrains its appetite? The coexistence of cold clouds and hot plasma raises similar questions. How do they avoid erasing one another? What balances the pressure, the shear, the radiation, the shock? The long filaments add a further riddle. Their rigidity hints at a framework, yet their distribution suggests a history of flares and winds. In this first layer of the journey, the methods matter as much as the pictures. The National Aeronautics and Space Administration provides the infrared heat maps that reveal hidden stars and warm dust. The European Space Agency extends the view into far infrared and sub-millimeter light, where molecules speak in narrow lines. The European Southern Observatory builds radio and infrared instruments on high, dry summits in Chile, linking dishes and mirrors into baselines that beat down blur. Together, they return not just snapshots, but time series, because the center is not a fixed diagram. Night after night, year after year, they look again. Small twitches in brightness, minute rotations in polarization, subtle shifts in spectral lines, all become the heartbeat measures of the compact source and its environment. Meanwhile, the larger scale remains the context. Spiral arms shepherd gas into lanes. The lanes feed the ring spills to the bar drives into the bulge, and within the bulge, streams split and merge like braided rivers. Shock fronts take energy from the gas and let it sink. Star formation removes gas and then returns some of it through winds and supernovae. The crowding increases the odds of close encounters, and close encounters build the angular momentum exchanges that carry matter inward. The whole system feels alive and hierarchical, a cascade that moves from gentle drifts to harsh accelerations as the radius shrinks. The narrator lingers on one quiet thought that is not a conclusion, but a pose of attention. The closer instruments look, the more the center behaves like a place where ordinary rules still hold, yet play at their limits. Relativity will matter in the inner steps. Magnetism will thread every fold. Chemistry will record past violence in complex molecules, carbon chains and ions that bear the memory of shocks. Already reflected light in certain clouds hints that brighter flares once lit the core in past centuries, leaving a delayed echo along dust walls like thunder returning from far valleys. Already, a hint of periodicity teases the records, not exact, not strict, but close enough to suggest that orbiting clumps or magnetic cycles might be at work. Yet nothing locks into finality. This is the correct mood for an entry chapter, a shape of the whole, a sense of inward pull, and a list of honest puzzles. The map now includes the bulge, the ring, the bar, the filaments, the streams, and the steady radio heart. The next descent will shorten the scale, stepping into the stellar ballet, where single orbits become clocks, where light bends just enough to trick straight instinct, and where the quiet engine at the center begins to show edges of personality. For now, first light has done its duty. The unseen has become seen in outline, and the outline points inward toward a place where space itself appears to gather and fold. Long before dust-piercing infrared eyes and horizon-scale arrays, the galaxy's center first declared itself to patient ears listening at long wavelengths. Radio astronomers swept the plane with antennas and found towards Sagittarius a tapestry of snarls and knots that refused to resolve into quiet background. At meter and centimeter bands, the Milky Way's midriff glowed with thermal whisper and non-thermal hiss, and within that din, a set of peaks and ridges stood out near the constellated teapot's spout. In those early surveys, the resolution was coarse, a finger painting of brightness that hinted more than it showed, but even so, the central few degrees looked over-bright, crowded beyond the norm, as if a city lay behind a fog. The next steps tightened the focus. Arrays that could combine many dishes into a single resolving power began to sharpen that city's outline. Filaments straight as rules appeared, narrow strands of synchrotron light cutting nearly perpendicular to the plane. Shells from old supernovae lit as partial circles. H2 regions where star birth ionizes gas dotted the map with soft blisters. And amid this bustle, a compact, stubborn voice sprang from the very heart. It did not flare like a variable star, nor did it sprawl like a nebula. It concentrated its power into a point-like source, with a spectrum that flattened toward shorter radio wavelengths, a behavior that set it apart from the diffuse haze. This was the puzzle that would later be named Sagittarius a Star, a name that tried to be casual and failed, because the source dominated curiosity whenever observers turned their arrays toward the center. To separate it from the surrounding structure required patience and ingenuity. The central region teemed with sources that overlapped in projection, and the interstellar medium between Earth and the bulge scattered radio waves the way ripples on a pond blur a reflected star. That scattering thickened and wavered, with wavelength making sharp images at longer meters nearly impossible. Observers attacked from many angles. They mapped at shorter centimeters where scattering shrank. They used baselines so long that Earth itself became part of the instrument, and they learned to model and subtract the blur. As the haze peeled away, more of the voice remained. Sagittarius A star was compact, beyond the reach of single dishes, variable only modestly at radio bands compared with high-energy WIMs, and embedded in a tangle of thermal arcs that formed a figure eight called the mini-spiral. The arcs themselves were not gentle streams, but ionized lanes where gas followed gravitational and magnetic rails curving toward the unseen center and then away. Their kinematics traced a complex dance influenced by tides pressure and field tension. The compact radio source at their crossing seemed less like a casual neighbor and more like the pivot around which the threads bent. Polarization gave another clue. Much of the radio bulge showed linear polarization consistent with synchrotron emission from ordered fields, especially within the long vertical filaments. Near the compact core, the polarization became subtle, its angles twisted by Faraday rotation along the long magnetized line of sight. Measuring that twist as a function of wavelength allowed astronomers to estimate the electron densities and field strengths in the intervening medium, and to constrain the immediate environment of the source. The rotation measure did not explode to impossible values. Instead, it settled into ranges that, when combined with models of the inner flow, implied that the mass actually crossing the smallest scales must be far below naive capture estimates. Even at radio wavelengths, the center whispered that it was underfed. Spectral shape deepened the impression. The flux density of Sagittarius A star rose from centimeter to millimeter bands, cresting in the sub-millimeter bump that would later become a cornerstone of horizon-scale imaging. But in the classic radio domain, the spectrum's slope, neither purely thermal nor purely non-thermal, hinted at a compact self-absorbed synchrotron source whose size shrinks with increasing frequency. Very long baseline interferometry confirmed exactly that at shorter wavelengths, the apparent size tightened, consistent with both intrinsic compactness and diminishing interstellar scattering. Those size measurements plotted against wavelength became a ruler that reached inward, one that later would be compared with the diameter of the dark ring traced by bent light near the horizon. Meanwhile, the map around the core grew richer. Arches and arcs glowed where young clusters poured ultraviolet light into nearby clouds. Bow shocks marked places where fast winds rammed dense clumps. The long non-thermal filaments crossed this scenery like taut harp strings, their remarkable straightness implying that magnetic tension did real work on scales of tens to hundreds of light years. The central thermal H2 regions curved inwards, their velocity fields measured through recombination lines that shifted with orbital motion, each line a thread pulling the eye toward the central knot. Across this field, Sagittarius, a star, held its station bright, but not blinding compact, yet not silent a metronome for the innermost dynamics, even before faster bands revealed its flares. The act of naming carried meaning. To call the source Sagittarius A star was to file it among many, but that catalogue label belied an intuition that grew with every map. A single persistent voice had begun to stand out from noise. The voice refused to resolve into a cluster, resisted interpretation as a supernova remnant core, and sat too still to be a wandering flare. Its steadiness over long spans, paired with subtle variability and a spectrum suggestive of a small hot magnetized pocket, aligned with the idea of an accretion flow around a dark mass. Even without direct images of horizons, radio maps fence the possibilities. Any alternative to a supermassive black hole would need to be as compact as the highest frequency sizes allowed, as dim in total power as the radio and sub-millimeter limits demanded, and as stubbornly central as the arcs of ionized gas required. The catalogues also documented time. Repeated surveys over years showed that while the filaments and shells changed slowly, if at all, the compact core wandered in brightness on timescales of days to months by modest factors. Such changes were not dramatic enough to mark explosions, but they were consistent with pockets of turbulence reconnection or variable feeding near the innermost orbits. On rare occasions, coordinated observations across radio and infrared found hints that small radio variations trailed infrared outbursts as expected, if a knot expanded and cooled after an initial acceleration of electrons closer in. These early correlations were weak by the standards of later campaigns, yet even as whispers, they linked radio behavior to the broader multi-wavelength pattern that would dominate the next decades of study. Perhaps most important long-wavelength surveys taught caution. The interstellar screen toward the galactic center can mimic size changes and smear fine structure, so every claim needed checks across frequencies and seasons. That discipline, born in the radio era, became essential when the world turned its many eyes to the center in other bands. It also taught optimism. If scattering and confusion could be tamed to reveal a compact core nested in a thicket of arcs and filaments, then more ambitious dreams such as measuring polarization angles around a ring of bent light were not fantasies, but distant milestones on the same road. Thus radio maps did more than reveal a bright, crowded center. They taught how to see through a troubled line of sight, how to subtract foregrounds without losing truth, how to isolate a point from a maze, and how to let a single persistent voice emerge from a chorus. They traced the first outline of a hidden heart and showed that the noise was not noise at all, but 1,000 useful signals layered together, each one a letter in a script that spelled out long before the letters were understood that the galaxy's core was both compact and commanding. From that realization, the rest of the story follows. Infrared windows open stellar orbits. Titan flares announce their erratic clocks. And finally, the horizon itself draws a dark boundary around a bright arc. But it was radio that first turned the murmur into a message and the message into a map. And in that quiet triumph, the mystery began to harden into fact. Dust that defeats visible light surrenders in longer wavelengths, and when astronomers turned eyes sensitive to the near and mid-infrared toward the galactic center, a hidden city brightened. The first wide surveys from space traced the bulge as a warm glow, but the revolution began when large ground telescopes learned to still the twinkle of the atmosphere. Adaptive optics sharpened images until individual stars could be separated in crowds once thought hopeless, and the central parsec resolved into knots and streams of light. What looked like fog became a cluster, and what looked like a smear became orbits. The instruments on the ground and in space complemented one another. The Very Large Telescope gathered sharp, deep images night after night. Keck Observatory added angular resolution and fast cadence. The Hubble Space Telescope offered stable, precise astrometry over years. The Spitzer Space Telescope mapped wider arcs and followed dust. And later the James Webb Space Telescope began to peel back even redder veils, revealing cooler structures and faint lines from molecules that cling to cold grains. In this window, stars became messengers of mass. A sparse handful close to the center traced loops so tight and so fast that their entire journeys could be watched across a human career. Their orbits were not guesses drawn through scattered points. They were paths measured year by year, and then night by night, with velocities inferred from Doppler shifts in spectral lines and positions fixed to fractions of a milliarc second against a crowded field. When these orbits were fit with the mathematics of gravity, they converged on a compact mass that could not be spread out without tearing the curves apart. The invisible body sat where the radio point called Sagittarius A star stood, and the match between radio position and the focus of infrared orbits linked two once separate stories. Around the fast stars lay swarms of others. The nuclear star cluster revealed age layers old metal-rich populations that testified to long patient building. Young massive stars in oddly coherent disks that must have formed in situ from gas that somehow resisted shear and shocks long enough to collapse, and dusty red wanderers that blurred the line between stars and clouds. Bright knots showed bow shapes as if running into winds that came from the center or from nearby hot stars, and those bows pointed like weather vanes toward pressure gradients. Fainter structures traced streamers of ionized gas that curved in three smooth arms around the center. In infrared light, Those streamers glowed with recombination lines, and with lines from heavier atoms, and their motions could be read from slight shifts of wavelength. The three arms, sometimes called a mini-spiral, were not calm rivers. They were lanes of material on intersecting orbits, sheared by gravity and nudged by magnetic tension, moving in a choreography that suggested repeated passages near the focus. The infrared view also carved fog into physics. Dust reddening across the field varied on small scales, and mapping that variation allowed extinction corrections that brought fainter stars into view and fixed their luminosities. Photometry in several bands let temperatures and sizes be estimated, and spectroscopy turned colors into line strengths that distinguish young hot stars from cool giants. In places, absorption features from ice and complex hydrocarbons told where cold clumps hid within brighter envelopes. At the same time, narrow emission lines at specific infrared wavelengths revealed the imprint of shocks and ultraviolet radiation. In regions where line ratios favored excitation by collisions, one could infer that streams had run into denser pockets. In regions where the ratios favored radiation, one could conclude that hot stars or a harder central source had carved cavities and warmed skins. The cold circumnuclear ring seen in radio and submillimeter maps as a necklace of dense clumps displayed an infrared face along its inner rim, warm dust arcs that sketch the edges of cavities, bright knots where tidal compression and external pressure together nudge gas toward collapse, and faint bridges that might be the first drips of matter falling inward. These bridges, when traced in velocity, showed twists that are hard to mistake for chance. They arc inward and downward toward the black hole's neighborhood, and then recurve under their own momentum, painting on the sky the outline of streams that will either feed the heart or be turned aside by pressure and field. Close to the center, where only a handful of stars dared to circle within light days of the focus, infrared kinematics wrote their names into history. One famous star dove near pericenter and emerged slower and redder in a way that agreed with gravitational redshift, and the argument about whether this effect could be confused by unseen masses faded as position measurements piled up. The pericenter advance of several stars, tiny forward slips of their closest approach points, began to appear as data gathered, matching the relativistic expectation within uncertainties and leaving less room for extended mass right next to the hole. The stars themselves were not only tracers, they were actors. Their winds fed the inner plasma with hot, fast material. Their radiation kept stream surfaces ionized. Their deaths left remnants that later would drift inward. Infrared monitoring caught short flares near the center, bright spikes that rose and fell within minutes to hours. These flares, seen alongside X-rays and followed by subtle dips at longer millimeter wavelengths, linked the infrared sky to the high-energy world. In the infrared band, polarization measurements during flares showed angle swings that aligned with the idea of orbiting knots or of magnetic loops rethreading near the last stable orbits. Away from flares, steady, polarized light from dust traced the magnetic geometry that threads cold clumps and lanes, revealing a field that bends with the bar on large scales, wraps the circumnuclear ring in a gentle harness, and sometimes launches straight radio filaments from sharp kinks. The young and massive stars in the central parsec posed a challenge and an answer. Their ages were too small for them to have migrated inward gently. They must have formed near their current locations or arrived in compact clusters that spiraled inward quickly. Infrared spectroscopy placed them in disks tilted with respect to each other, a sign that gas streams entering the ring at different longitudes and angles had at least once cooled and settled into organized planes before fragmenting into stars. These disks themselves bend under torques and precess, and their evolution promises near-term changes in where winds and radiation drive flows. The infrared window also caught oddities that refused easy classification sources that brightened as if dusty envelopes were heated, then faded. Objects that stretched as they approached the center, turning from star-like knots into extended smears, and then recovering shapes after pericenter, as if wrapped in gas that was tugged by tides and then recondensed. Such passages offered experiments designed by nature when a dusty, perhaps star-enshrouded object grazes the inner flow. The response in infrared and in X-rays tests how gas and field couple and how quickly electrons are accelerated. The greatest gift of the infrared was continuity. Night after night and year after year, the same instruments could return to the same stars and streams and remeasure their positions and lines. From these remeasurements came accelerations, and from accelerations came masses and constraints, and from constraints came the confidence to match the black hole's ring measured by radio with the mass demanded by gravity at larger radii. The window is still widening. Longer wavelength infrared now reaches deeply into the circumnuclear ring to map molecules that register shocks with exquisite sensitivity, while shorter wavelength infrared with sharper adaptive optic spots, new fast stars that may one day pass close enough to feel frame dragging. The city that infrared light revealed is not quiet or static. It is a metropolis with traffic laws written by gravity, with side streets set by magnetism, with weather made of shocks and winds. Dust no longer hides its shape, and the shape sketch orbits that circle something compact and dark. As each orbit closes, curiosity sharpens, the invisible mass is real and central. The dancers obey curves drawn by curved space-time, and the window that opened through dust has turned from a novelty into the principal way to watch the outline of an invisible heart being traced by stars that do not guess but know. At the very center where dust thins under the push of longer wavelengths, and where radio and infrared positions can be tied to the same point on the sky, a few dozen bright hot stars perform a dance that has become the most precise scale in the galaxy. Night after night, year after year, telescopes steady their blurred vision with controlled optics and return to the same crowded field, measuring positions to a fraction of 1,000th of an arcsecond and velocities from the tiniest shifts in spectral lines. Out of those measurements grow orbits so tight and so fast that a human lifetime can hold several passages around the unseen focus. The curves are not sketches drawn to taste. They are traced in real time as each star sweeps from slow distant arcs into quick close turns and back out again. Fitted with the mathematics of gravity, these loops insist on a single conclusion. A mass of nearly 4 million suns hides within a volume smaller than the inner lanes of our own planetary system. Spread that mass into any plausible cluster of dark remnants, and the cluster would evaporate or collapse in a blink compared with the age of the galaxy. Compress it into any exotic object with a surface, and the surface would glow or reflect in ways that the sky refuses to show. The dancers demand an object with no visible skin, a horizon rather than a crust. The precision of the ballet reaches beyond the statement of weight. As a star dives toward closest approach, its clock slows in the deep well, and its light slides to longer wavelengths. Spectrographs record that gravitational redshift against models that include every known nuisance, and the match lines up to the limits of measurement. When the same star returns years later, the ellipse it draws on the sky has rotated forward by a small, stubborn angle. That advance of the closest approach is the signature of curved space-time written into celestial mechanics, and although a faint haze of unseen mass in the inner cluster tugs backward a little, the forward push remains, and the net motion agrees with the theory that joins mass and geometry. These two tests together, the time dilation seen in the spectrum and the periapse advance seen in the sky, turn the nuclear star cluster into a courtroom where ideas about gravity either pass or fail. Around the fastest dancer move others with different tempos and shapes, and their diversity becomes a diagnostic of the environment. Some orbits are nearly circular and live farther out. Others are steeply elongated and dive deep. If a dense swarm of stellar mass black holes or neutron stars crowded the inner light year, the many small tugs from that swarm would smear the orbits of the visible stars, broadening the distribution of shapes over time through a process of resonant relaxation. The data allow some hidden mass, but not enough to erase the relativistic advance or to turn the orbits into a soup. In this way, the ballet weighs both what is obvious and what is not, setting limits on dark matter that could in principle rise toward the center and on the number of compact remnants that a history of star birth and death might have piled into the core. The dancers also tell how they arrived. Many of the brightest are young and massive, too young to have drifted inward by gentle friction through the crowd. Their orbits arrange themselves in patterns that suggest past disks, planes of gas that cooled and settled, despite shear, then fragmented into stars that kept the memory of the plane in their first paths. Those planes do not last forever. Torques from the central mass from nearby clusters and from magnetic pressure bend them and precess them, turning order into a controlled chaos whose traces remain in the tilt and twist of present orbits. The oddest wanderers are dusty and red, changing shape as they approach and recede as if cloaked in gas that is stretched by tides and then gathered again, or as if two stars wrapped in a common envelope had been nudged into a path that skims the inner flow. Such objects become planned experiments as one grazes the core flares in high-energy light and angle swings in polarized near-infrared can test how quickly a thread of plasma responds when a clump pushes through. The ballet does not end at the core, it throws partners outward. When a binary star strays too near the black hole, gravity can break the pair, binding one star into a tight new orbit and flinging the other out at speeds that can exceed the escape speed of the galaxy. The fast exiles, now seen far in the halo, point back to the center by their ages and direction's silent testimony to close encounters on scales too small to image. By counting such stars and reading their clocks, one can infer how often the core reshuffles pairs, and thus how crowded the inner parsec truly is, with both visible and invisible masses. Technique is as important as theory in this dance. Absolute positions in the infrared must be tied to the radio frame that anchors the compact source at the center, so that motions are not measured against a drifting background. Dust reddening must be mapped on scales smaller than the separations between stars, so that luminosities and line strengths are corrected without bias. Spectroscopy must resolve not only broad lines from hot atmospheres, but the tiny Doppler shifts that mark tens of kilometers per second near pericenter. Even the shape of a star's point spread function becomes part of the physics, because a slightly skewed image can masquerade as a slight positional shift if not corrected. The discipline built from these details has turned the central parsec into the best calibrated dynamical laboratory beyond our solar system. With calibration comes ambition. Observers now search for a radio pulsar in a close orbit, knowing that such a clock would turn the center into a place where the spin of the black hole could be measured through frame dragging and where the exact shape of space-time could be tested through the quadrupole moment that only a true spinning black hole should have. Short of that dream, the stars themselves may yet speak to spin. If a star is found with a period of only a few years, and a pericenter within a few thousand gravitational radii, the slow turn of its orbital plane could betray the twisting of space-time by the hole's rotation. Matching such a dynamical spin to the spin hinted at by the bright crescent's polarization and brightness asymmetry would ask whether two very different instruments are seeing the same angular momentum. The answer would either lock the portrait into place or reveal a mismatch that points to structure in the inner flow that has fooled the light. The ballet also keeps time with events that reach beyond pure mechanics. On rare nights, a strong near-infrared flare arrives near the time a fast star sweeps through its closest approach, and though the two may be unrelated, their pairing focuses attention on how energy is stored and released near the last stable orbits. If hotspots truly orbit there, their characteristic times should scale with mass and with distance from the horizon in a way that can be compared against the orbital periods of stars just outside. Any harmony or discord between the clocks would teach where the boundary lies between coherent orbits and turbulent flow. In all of this, the most striking feature is the poise of the evidence. The stars accept simple gravity as their master, and then reveal small exact deviations that speak for the deeper law. They circle an object that refuses to show a surface, and yet sculpts the light around it into a ring. They live in a city where supernova scars, magnetic filaments and cold clumps all press upon their paths, and yet their curves remain smooth enough to weigh what no eye can see. The tension rises, not because the conclusion is in doubt, but because certainty lifts new questions. How thin is the veil of unseen mass still permitted by the data? How quickly do plane-like groups of young stars dissolve under torques? How often does a binary wander into the loss cone that leads to separation and exile? How near to the horizon will the next discovered star pass? And will its plane tilt under the twist of space-time in a way that even a cautious analyst must accept? The stellar ballet began as a way to find a mass, and it has become a way to interrogate a law. It is not a spectacle staged for our benefit, yet it reads like a play in acts, entrance on wide arcs, descent into tight turns, red-shifted chords at pericenter forward slip of the ellipse long exit to a new aphelion, and then the curtain rising again on the next passage. Each repetition leaves less room for alternatives and more room for precision. The invisible heart remains invisible, but the dancers keep pointing to the same center, and the center they point to has the properties of a real black hole. The floor beneath them is curved, the lights above them bend, and the orchestra that sets their timing is gravity itself playing a score that is spare, exact, and inexhaustibly beautiful. The heart of the galaxy does not simply glow, it startles. Every so often, and with no reliable warning, high-energy flashes leap from the region around Sagittarius, a star brief spikes that lift the center above its usual quiet, and then let it fall back into hush. orbiting eyes built to see the hottest light catch these eruptions and pass them on the National Aeronautics and Space Administration's Chandra X-ray Observatory give sharp pinprick views. The European Space Agency's XMM Newton gathers long patient exposures. The Nuclear Spectroscopic Telescope Array listens higher in energy where rare hard photons land. The Neil Gehrels Swift Observatory keeps an ongoing watch ready to slew and witness a burst. Across years of attention, a pattern refuses to form. Flares rise within minutes, decline within roughly an hour, and vary by orders of magnitude in brightness. They cluster some weeks, then vanish for long stretches. They hint at rhythms that dissolve when new data arrive. Each new flash becomes a single drumbeat in a piece without a clear meter, and unease spreads as the timing offers no stable clock to fold the light upon. During a flare, the spectrum hardens, telling of electrons pushed to extraordinary energies, and the brightness curves sometimes show substructures, brief plateaus, and shoulder peaks, as if multiple knots of plasma ignite in quick succession within a region no larger than the orbit of Mercury. The same hours occasionally deliver paired outbursts, one in near-infrared and a later one in X-rays, or the reverse, inviting the idea that a common population of particles radiates first through synchrotron emission and then upscatters photons through inverse Compton processes. At other times, the bands move together as if they are different windows on a single spark. The fact that Sagittarius A star ordinarily wastes its available fuel makes each flare stand out. All the more the baseline is a whisper. The outburst is a shout, and then the whisper resumes. Theories line up at the doorway. Magnetic reconnection, where twisted field lines snap and stitch and dump stored energy into particles, would naturally be sporadic and violent. This is seen in the Sun, and scaled to a black hole it could drive the erratic timing and hard spectra. A compact hotspot orbiting close to the point of no return would brighten as it swings toward the observer and dim as it recedes its path, modulated by the bending of light and the time dilation of intense gravity. Such a spot would leave imprints at orbital timescales of tens of minutes, and indeed some flares show suggestive wiggles near those durations, though none hold long enough to be declared a rule. Small ejections, plasma knots launched on narrow tracks, might light up as they expand and cool their energy budget parceled out between X-rays, infrared, and submillimeter. Even turbulence at the inner edge of a feeble accretion flow could grow and collapse like weather-building pressure in pockets until a threshold tips and energy dumps into electrons, only to disperse again. Each idea fits some events and slips on others, and so the catalogue lengthens without closing. Observers have learned to call for coordination, lining up facilities across wavelengths and continents to watch the center together for nights, days, and weeks. When a flare begins, a chain of instruments pivots. Infrared adaptive optics on large telescopes catch the rise. Millimeter arrays listen for later echoes. X-ray observatories measure the energy slope with fine timing. Sometimes the result is a crisp sequence: infrared first, then X-rays, then a sub-millimeter dip as heated material becomes optically thick. Sometimes X-rays strike alone. Sometimes multiple small flares blend into what looks like one wide event. A handful of remarkable nights show polarization swings in infrared, hinting that magnetic fields are rotating, or that the emitting region is orbiting the black hole, and at nearly the same moments the X-ray light curve stutters in step. Yet the next season brings flares with different choreography, and the suspicion grows that the center is running more than one script. The spatial scales implied by the fastest changes are tight within a few tens of microarc seconds, as seen from Earth, a space that abuts the event horizon size inferred by very long baseline interferometry. The energy required to accelerate electrons to radiate X-rays through synchrotron processes is extreme, and their radiative lifetimes under such conditions are measured in mere minutes, which naturally matches the sudden rise and fall, but also demands ongoing acceleration during the flare. Inverse Compton scenarios relax the particle energy demands, but require a bath of lower energy photons to boost, which invokes the local infrared field or the sub-millimeter photons from the accretion flow. Either path circles back to the same uncomfortable center. The engine is small, close to the hole, and complicated. Over longer times, the average flare rate seems to wobble. There are months when bursts pile up and months where nothing happens. When a gas cloud on a highly elliptical path moved into the central region some years ago, many anticipated a feast of flares as fresh material trickled inward. If there was an effect, it was modest, a reminder that the inflow from parsec scales takes time to reach the last stable orbits and that local processes can easily dominate. Elsewhere in the surrounding parsecs, echoes of ancient activity appear in fluorescent lines within cold molecular clouds, as if past more powerful X-ray flashes lit the gas and left delayed reflections. If those echoes are real, then the present is a lull, and the engine has a history of louder eruptions, with the sporadic modern flares being small embers falling from a fire that once roared. The data invite a deeper test of gravity too, because the fastest variations probe the innermost stable orbits directly. If a hotspot or a reconnection site rides those orbits, gravitational lensing time dilation and Doppler boosting will sculpt the light curves in specific ways. Analysts fold the data with tentative periods, search for phase-dependent changes in polarization angles, and stack many events to look for a hidden rhythm. The results are tantalizing but not decisive, as if the system insists on rearranging itself before any regularity becomes clear. Even so, each flare plotted and archived becomes a marker against which future theory must align. What is most striking after many years of vigilant watch is that the flares seem to say more about how the black hole is fed than about the black hole itself. A sparse accretion flow dominated by hot, rarefied plasma may naturally fragment and reconnect a kind of stellar weather that sometimes builds thunderheads and sometimes clears. The narrow margins where magnetic fields and plasma pressure trade dominance are perfect places for sudden energy release. In that picture, the lack of a strict clock is not a failing, but a signature. The engine is a living fluid near an overwhelming gravitational well, and its history is written in chance. The steps toward a clearer answer are obvious and hard. Denser coverage with coordinated multi-wavelength campaigns will tie the timing across bands more tightly. Faster X-ray timing will catch the shortest flickers and test for orbital features. Polarization movie making at infrared and sub-millimeter will sketch magnetic geometry in motion, and higher resolution horizon scale imaging may one day catch a flare's glow tracing a loop around the black hole. Until then, the record of flashes remains a field log of sudden mornings and sudden nights at the center, a diary of light that refuses to march but keeps returning each time with a slightly different tone, each time reminding the watchers that the galaxy's hidden heart chooses its own beat. The inner few hundred parsecs of the galaxy gather matter into a dense and restless environment where extremes crowd together. cold molecular clouds, heavy with dust, drift in lanes that curl like smoke around the bulge, while nearby a hot, thin plasma races along narrow channels, each medium ignoring the other, until a shock or a shear forces contact. The broader region, known as the central molecular zone, carries gas with densities far above the disk average, and with motions that refuse to settle, so that even the most massive clouds look stirred and frayed. Within these clouds, the thermometer points to tens of degrees above absolute zero, a realm where molecules survive and grow, yet the same sky also holds gas heated to millions of degrees, stirred by supernova shocks, fast stellar winds, and magnetic tension that snaps and releases energy. Chemistry becomes a map in this terrain. Lines from hydrogen cyanide, silicon monoxide, carbon monosulfide, formal cation, and long carbon chains rise from the cold lanes, their relative strengths recording where shocks have shattered dust grains, where cosmic rays have driven ionization into depths that starlight cannot reach, and where ultraviolet light from young clusters has gnawed at cloud edges. The triatomic hydrogen molecular ion appears in absorption and tells that ionization rates near the center are elevated by orders of magnitude, which means that even the coldest pockets feel a buzz of high-energy particles moving through. Methanol and ammonia trace dense cores within giant clouds, some of them gathered into string-like pearl chains along orbital paths, and their line ratios insist that the gas is warm by the standards of the outer disk, as if every cloud has been kneaded by passing shocks. At the same time, a web of hot streams courses through and around this cold material. X-rays and radio recombination lines reveal pockets and corridors of shock-heated plasma that thread the bulge, carrying sound speeds far higher than the escape velocity from a single cloud. Where these corridors run, the pressure they exert can confine cold gas into filaments and sheets, giving the appearance of improbable long straight structures that hold together against the pull of gravity and differential rotation. The magnetic field adds its own order. Long radio filaments rise nearly perpendicular to the plane, some of them extending hundreds of light years, suggesting a large-scale magnetic scaffold woven through the region. Polarization measurements in radio and sub-millimeter light show that dust grains in the cold clouds align along field lines that bend around arcs and lanes, while the hot streams seem to follow a stiffer, more vertical configuration. At their crossings, energy transfers in complicated ways. A strong field can cushion a shock, allowing a cloud to survive a blow that would otherwise shred it, yet the same field can funnel gas into narrow throats, where it accelerates and heats. Gravity from the central mass and from the stellar bulge tilts the table so that much of the gas chooses inward-leaning orbits. A barred potential in the disk steers matter along leading edges into rings at a few hundred parsecs, then again toward a circumnuclear ring only a few parsecs from the black hole, where cold clumps orbit in a constantly perturbed track that looks serene from far away and stormy up close. Along the way, dust lanes become shock fronts. Carbon monoxide brightens, and certain species like silicon monoxide spike as grains are crushed and sputter their silicon into the gas. In the same neighborhoods, ultra-hot plasma emits hard light that points to recent heating, either from multiple small supernovae whose shells overlap, or from widespread turbulence that cascades energy down to tiny scales where it dissipates as heat. Star formation in the center complicates the picture and clarifies it. Despite high densities, The rate at which cold gas turns into stars remains lower than in equally dense clouds farther out, which hints that turbulence, tides, and magnetic support raise the threshold for collapse. Yet where collapse does proceed, it often does so in bursts along arcs and rings, leaving clusters that drive winds and carve bubbles. Those winds feed the hot streams, which in turn confine other clouds, and sometimes trigger the next round of collapse by squeezing a marginally stable core. A feedback loop grows, but it is patchy and time-dependent, so that in one sector, a hot bubble scours gas away, while a neighboring sector sees a dense filament pinched and cooled into stars. Infrared observations find ice features in dust that survives deep inside the cold clumps, while millimeter interferometers resolve substructures that look like beads, each separated by a distance set by the balance of self-gravity and pressure. Just outside those beads, spectral lines widen and split, marking shear and crossing flows. This duet of cold and hot carries a faint rhythm in time. There are hints that the cold ring at a few parsecs intermittently feeds the black hole by letting a clump overrun its orbit and fall inward along a stream that becomes ionized and heats on the way, shining in near infrared and then in high energy light as it approaches the last stable orbits. Elsewhere, light echoes in surrounding clouds record more powerful heating episodes in the past, as if centuries ago the center shone more brightly and bathed the cold lanes in hard photons that left chemical signatures still fading now. The idea of time-linked coincidences takes root here. Spectral changes in cloud tracers line up with past flares in hard light, and models that include delayed illumination of distant gas produce maps that match observed bright patches. In this laboratory, physics that is hard to arrange on human scales plays out on an epic stage. Magnetized shocks push ion-neutral drift that alters chemistry and heats selected layers of a cloud without destroying it. Turbulent eddies cascade energy from giant structures down to the size of a star-forming core, setting internal velocities that resist collapse until a chance alignment or a ram pressure wave tips the balance. Cosmic rays energized by many overlapping supernovae and by magnetic reconnection near the black hole penetrate deeply and alter the ionization fraction, so that ambipolar diffusion and magnetic braking change their pace. Even dust grains far from passive charge and discharge align and realign, shatter and coagulate, rewriting the opacity that governs how radiation slips through. The narratives of cold and hot refuse to separate cleanly because they share boundaries everywhere. Along the edges of a giant molecular complex, thin skins glow in lines that demand hot electrons, while just behind those skins, molecules reassemble. At the heart of a hot corridor, islands of dense gas survive like stones in a stream, casting wakes where vortices spin and vorticity curls magnetic lines into ropes. Farther out, gigantic lobes above and below the plane tell of energy launched from the center. Long ago, a memory of outflows that likely rose when the cold ring delivered more fuel, or when a starburst filled the inner kiloparsec with overlapping winds. Those old pushes still sculpt the pressure field in which today's clouds move. The destination of all of this motion remains inward, not as a smooth river, but as a mosaic of steps and stalls. Gas shifts from atomic to molecular, from diffuse to clumpy, from warm to cold, then back to warm and hot as shocks and radiation catch it. Some fraction reaches the circumnuclear ring and survives as a chain of clumps that pass momentum among themselves like dancers occasionally letting one stumble inward. Other parcels fail to cross resonances and instead ride around the bulge for many orbits enriched by chemistry and stripped by tides. To observe this scene is to accept contradiction as a clue rather than a failure. Cold clouds and hot streams coexist because the region never reaches equilibrium. It is instead a driven system constantly supplied with fresh gas from the bar and constantly disturbed by gravity-magnetic fields and explosions. The result is a stack of layers each with its own temperature and density and chemistry woven together by motions that shift faster than a single map can capture. In the center of this weave, the black hole waits, sometimes hungry, sometimes quiet, always shaping the stage even when it does not speak. The puzzles multiply, but so do the tools, higher resolution mapping of molecules that trace shocks and density polarization movies that sketch field lines in motion, sensitive hard light surveys that follow the hot corridors as they brighten and fade. Together, they promise a clearer view of how the cold survives in a furnace, and how the furnace is fed by winter air, and of how both lead in time to the next outburst that will light the dark heart again. The central bulge of the galaxy is crossed by lines that are not made of stars or gas, but of force, and radio instruments reveal their outlines as if a hidden loom were holding the region in a taut weave. Long, narrow filaments rise almost straight from the plane, some extending for hundreds of light years, with widths so slight that they press the limits of resolution, and they shine not with heat, but with the steady glow of charged particles that spiral in magnetic fields. Their light is linearly polarized, which tells that the emission is synchrotron radiation, and that the field that guides the particles is organized rather than tangled. Many of these filaments stand nearly perpendicular to the disk, a forest of fine wires crossing the haze of the bulge, though in places they bend like reeds where they meet lanes of cold gas, or where they pass through pockets of hot plasma. In deeper mosaics, what first looked like single cords resolve into bundles of close threads, offset but parallel, as if they were strands in a cable. Elsewhere, the filaments cross at high angles, forming meshes whose nodes mark regions where field lines may reconnect and release energy. Pattern hunting begins with these shapes and then follows the clues in how the light is polarized. The plane of polarization swings along a filament, implying that the field within it keeps its direction over long distances. Across the wider bulge, the polarization maps twist, as if a grand spiral field were wound around the center, with sign changes that suggest the field flips direction across large scales. Dust grains offer another probe. In submillimeter light, their polarized glow traces field lines frozen into cold clouds, and those lines sometimes curve along arcs that embrace the bar, and sometimes feather into the straight rungs that connect to the vertical filaments. In a few dense clumps, the tiny splitting of spectral lines gives direct estimates of the field strength, and the numbers are not small. They are a few thousandths of a Gauss, strong enough that magnetic pressure rivals the pressure of the gas itself. The picture that gathers from all these threads is of a lattice that bears weight. Magnetic pressure props up parts of the bulge against collapse, and magnetic tension channels motion along preferred paths. When a fast flow meets a stiff field, it cannot simply shove the lines aside. Instead, it slides along them, and the sliding gathers gas into narrow lanes. That is how ordered fields draw visible borders in an otherwise turbulent region, sketching long, straight edges across a roiling background. The thinness of the filaments demands that losses be balanced by supply. electrons radiating in such fields lose energy and would fade in times shorter than the lifetimes suggested by the great lengths of the chords. Therefore, some engine must accelerate new particles in or near the threads. Magnetic reconnection is a natural candidate when field lines of opposite direction are forced together by large-scale shear from the bar, or by local turbulence they can break and recombine, dumping stored magnetic energy into fast particles. Shocks from stellar winds and supernova remnants provide another path, pressing and amplifying fields while boosting electrons. In some places, the filaments appear to anchor in arcs of hot ionized gas that curve like bows, and in those places the brightness may be fed by waves that bounce between the arc and the filament. In other places the cords seem to spring from the edges of cold lanes. Where a dust ridge bends, a straight thread launches from the kink and runs upward, hinting that shear at the boundary of cold and hot has stretched flux into a taut spine. The broader field has memory. Above and below the plane sit vast faint lobes that recall ancient eruptions from the center, and many filaments lean toward those plumes as if they were rungs on ladders that once carried energy outward. If the lobes were inflated by past outflows from the black hole or by a burst of star formation, the flows would have draped the magnetic field into global arcs, and the filaments could be the places where those arcs touch dense gas and light up. Even today, faint halos of polarized emission extend far from the plane, and their smoothness contrasts with the crispness of the cords below, a sign that the lattice's nested large frames hold smaller girders. The lattice does not merely sit, it acts. In cloud after cloud, the direction of the field correlates with the long axis of the structure, which hints that gravity and magnetism dance together. Where the field lies across a filament of cold gas, collapse is slowed, and star formation waits until turbulence and ambipolar drift open a path. Where the field runs along a dense ridge, flows slide inward and can pile up mass until a threshold is crossed, and stars are born in a string of pearls. At the same time, the field serves as a highway for energetic particles, guiding cosmic rays through the bulge and into the halo, spreading heat and ionization along preferred routes. Those particles alter chemistry, change the balance between ion and neutral in cloud skins, and set the conditions for friction between the two components, which in turn shapes how the field and the gas couple. In this way, the magnetic geometry becomes a silent regulator that sets the tempo for the cold and the hot both. Time adds movement to the shapes. Some filaments brighten or dim over years as if their engines of acceleration start and stop. Others stay steady for decades, behaving like light pipes with a constant feed. In a few cases, small knots seem to slide along a thread, which a watcher could read as waves running down a taut string. Those waves could carry energy and information across dozens of light years, stirring plasma where they dissipate. Crossings are special. Where two threads intersect or pass very near each other, small outbursts appear in light curves. Polarization angles flip and faint halos bloom, as if reconnection at the junction were briefly heating the local plasma. These events echo the erratic flares near the black hole on much larger scales, supporting the idea that the same fundamental process of field rearrangement operates from the inner orbits out to the bulge. The portrait that emerges from multi-wavelength mapping is therefore of a coherent but complex frame. Low-frequency radio light paints a smooth background that follows the average field. Higher frequency radio light sharpens the individual chords. Infrared polarization draws field lines inside cold, dense lanes. X-rays mark pockets where hot pressure shapes geometry and forces the field to bow or buckle. Put these pieces together, and a picture appears in which a largely vertical system of strands rises through the central region, while a set of horizontal arcs wraps the inner rings, and at their crossings, the system trades energy through reconnection and waves. Such a skeleton shapes how matter falls toward the black hole. Gas that tries to tumble inward must thread the field. As it does, torsion builds, and tension can either break the flow and park it in rings, or snap and fling material outward along funnels. This may help explain how the center can be both underfed and yet ready for sudden releases. The field stores angular momentum and energy in its twists, letting gravity collect matter along the rails, and then a change in topology opens a gate. When the gate opens, a stream dives inward, or a knot is thrown upward, or both, and the system reknits itself. The lattice is not rigid, and it is not permanent, but it persists, because the drivers that build it are steady: shear from the bar, inflow from spiral arms, feedback from young clusters, and the deep pull of the central mass. Seen in this way, the long filaments are not curiosities at all, but the visible grammar of an invisible order. They show where the field is strong, where flow is channeled, where energy is stored, and where it will be released. Future eyes will trace their strands in finer detail, measure their polarization angles as they change with time, and watch knots march along their lengths, turning still images into a kind of slow movie. In that movie, the framework may at last reveal the script of the bulge, how lines of force and lanes of matter co-author the story of a quiet yet restless heart, how patterns endure while details flicker, and how the hidden lattice both supports and restrains the galaxy's central breath. Far from the center, where the disk looks calm in wide views, spiral arms sweep like slow rivers of stars and gas, and their gentle pressure waves gather dust into lanes that glow softly. Those arms do not end in space. They lean toward the bar that cuts across the inner disk and deliver their freight to its leading edges. There, the smooth flow becomes a fast descent down a tilted plane of gravity. The bar's elongated mass distorts the potential stretching orbits into long loops aligned with its length and steering clouds toward shocks that lie just inside the leading edges. In those shocks, the ordered drift of gas is upset, density jumps, dust reddens, and molecules that are fragile in quiet space flash into visibility, because collisions become frequent. The shocks also take something more precious from the gas than heat. They steal angular momentum. With each jolt, the gas gives up a little of its tendency to circle and gains a little more tendency to fall inward. This is how the galaxy nudges its own breath by sculpting orbits so that matter slides inward even as it orbits trading spin for descent in a series of small bargains. As clouds ride the bar, their paths change character. Farther out, the orbits are elongated along the bar, but deeper in the same gravitational sculpture admits a family of orbits aligned almost perpendicular to it. The meeting place between those two families is not tidy. It is a region of crowding where streams jostle and cross, and where shocks curl into bright dust lanes that run to the ends of an inner ring. That ring, a few hundred light-years across, is a traffic circle for interstellar matter. Gas arrives along two or more major lanes, hits the ring near preferred contact points, and then streams along it, sometimes piling up in lopsided clumps that feed bursts of star formation. The ring is not perfectly round, and it is not perfectly steady. It breathes in response to the bar's slow rotation and to the continual arrival of new material. Where gas lanes strike it, turbulence intensifies and magnetic fields bend, setting the stage for transient arcs that light and fade as clouds pass the gates. Within the ring, the scene tightens again. Orbits shrink, become more circular, and stack into a disk where the balance between rotation and pressure grows delicate. The disk is hardly uniform. Cold lanes draw together into beads. Hot corridors trace the scars of recent feedback, and between them, intermediate layers rise and fall like surface waves. The net effect remains the same. Momentum gathers along the ring, while small amounts bleed inward through a tapestry of torques, drags, and shears. Gravitational torques from the bar do much of the heavy lifting at large radii, but inside the ring, other hands take over. Spiral density waves arise even on these small scales, their crests wrapping around the center like the faint ribs of a shell. Each rib is a pressure ridge where gas slows crowds and lets go of another pinch of angular momentum. Viscous forces born of turbulence add their nudge as eddies mix fast and slow gas and spread rotational energy from one stream to another. Magnetic stresses tie distant parcels together so that a change in one place can release tension in another, allowing matter to slip a little closer to the heart. Shocks at spiral ridges are especially important. Seen in near-infrared light as dusty filaments, and in radio light as lines bright in dense gas tracers, they cut across the inner disk at angles that point toward the center. Gas meeting these ridges is pressed and heated. Some of it forms stars in the compressed wake, some of it is diverted along the ridge toward the ring, and some of it loses enough angular momentum to plunge inward on a track that curves like a question mark into the circumnuclear zone. The phrase sounds serene, but the reality is restless. The circumnuclear ring at a few parsecs in radius is where the flow becomes a whisper compared to the roar of the outer shocks. Yet this whisper decides the fate of the next steps. Cold clumps travel around the ring as if they were beads on a wire, exchanging pushes and pulls that sometimes kick one off the track into a stream that spirals toward the black hole. The stream ionizes as it approaches the intense radiation and hot plasma of the inner region and becomes a visible tracer of motion. Even nearer, within a fraction of a light year, the flow becomes a set of arcs and lanes that trace a miniature spiral, suggesting that the same logic of waves and shocks repeats at a smaller scale. If the outer arms were rivers and the bar were a sluice, the inner spirals are braided creeks running over stones with some water sinking away between pebbles and some leaping ahead in sudden drops. Star formation keeps rewriting the map as it goes. Where gas crowds into the ring and holds its density long enough, gravity wins and clusters ignite. Those clusters push back with winds and light punching holes through the cold medium and adding hot pressure to the inner disk. The pressure creates new gradients that tilt the local balance of forces, altering which paths are easy and which are hard. Outflows above the plane carry away some of the spin and heat, which indirectly makes it easier for the remaining gas to drift inward. On longer timescales, the births and deaths of stars modulate the inflow like a slow drum behind the quicker rhythm of shocks, never in perfect step, never quite the same twice, but always tending to clear the way for a fraction of the mass to drift to smaller orbits. Gravity from the bulge and the bar is not the only guide. The magnetic lattice described earlier serves as a subtle set of rails. Where straight filaments cross a dusty lane, gas finds a path of least resistance along the field and is drawn into thin streams that angle toward the center. Where the field runs transverse to a flow, it can hold a cloud together as it rounds a sharp curve, preventing it from shredding, which paradoxically allows it to travel deeper before dispersing. Polarization maps show places where the field lines bend around the ring as if wrapping it in a loose harness. The harness does not pull continuously. It tightens and loosens as turbulence and reconnection change the topology. When it tightens, matter is shepherded along preferred routes. When it loosens, material spreads and stalls, waiting for the next rearrangement. The arms themselves evolve. They are not fixed sculptures, but standing waves maintained by the collective gravity of stars and dark matter, and by the response of the gas. As the pattern slowly turns, resonances migrate. The borders where one type of orbit gives way to another shift, and with them the location of the ring and the angles of the inboard shocks. Over many rotations, the inner pathways redraw themselves, making the history of inflow a layered palimpsest. Ancient rings leave traces in star clusters that drift outward, while newborn rings collect fresh gas and write new arcs across the same sky. The overall direction, however, remains constant inward. Momentum gathers from a sprawling disk and is siphoned toward the core by the combined action of gravity shocks, waves, turbulence fields, and feedback. The journey is not smooth, yet it is relentless. Step by step, cloud by cloud, parcel by parcel, the system converts orbital spin into central weight. Sometimes the path is patient, storing matter in rings for long intervals. Sometimes a path opens suddenly, and a stream tumbles inward in a luminous rush that announces itself as a series of flares or as a temporary brightening of hot light near the hole. In the long view, the arms are the outer expression of a deeper logic. Structure channels flow, and flow changes structure. Each inward bend of a lane tightens the potential. Each burst in the ring readjusts the pressure field. Each magnetic strand that anchors to a dusty arc resets the rails. The result is a living funnel, whose mouth is wide in the disk, and whose throat narrows near the horizon of the black hole. What seems like a diffuse galaxy from afar is in truth a machine with moving parts, each part touching the next, each part leaning inward. The mystery is not that matter falls. The mystery is how the galaxy uses its patterns to persuade matter to fall in such intricate, beautiful steps. For decades, the weight at the center was an inference from motion, a deduction drawn from stars that raced along tight curves and then returned on schedule, their arcs and periods adding up to a single demand. There is an object of nearly 4 million times the mass of the Sun compressed within a region no larger than our solar system's inner lanes. That constraint grew sharper as years of measurements accumulated. Each time a fast star swung close to the focus of its long ellipse, the speed spiked, and the timing of those spikes traced out the mass as surely as a scale. The paths also began to show subtle features that pure Newtonian gravity could not account for, gentle advances of closest approach that whispered of curved space-time. Yet even as the mass estimate settled, the nature of the thing that held that mass remained a question. A cluster of dark remnants could have hidden there, or a ball of exotic particles might have held itself together by forces we barely suspect. The case for a supermassive black hole was strong, but not complete. The missing signature would need to speak from the very edge of the unseeable, where light bends and time slows, and the concept of surface gives way to a horizon. That signature arrived when radio dishes spread across Earth learned to act as one eye. The Event Horizon Telescope Array reached a sharpness that human sight had not held before by combining signals gathered across continents and recombining them with exquisite timing so that the effective mirror had the size of the planet. With that reach, the region around Sagittarius, a star became resolvable not as a point, but as a shape. The resulting picture was not a photograph in the ordinary sense, but a reconstruction guided by physics and by the careful stitching of wavefronts. What it revealed was a bright lopsided ring surrounding a dark interior. The ring was not a solid object. It was light from hot plasma bent into a circle by gravity, with one side magnified and brightened by motion toward us and by the curvature of space-time. The dark interior was not a shadow in the usual way. It was a deficit of light from directions where photons fall inward and fail to escape. The size of the ring and the diameter of the darkness were not arbitrary. They were set by mass and by how fast the central object spins. When the measured ring matched what general relativity predicts for a black hole of the mass derived from stellar orbits, a long arc of work closed. At last, there was a horizon-scale anchor to the invisible. Certainty bred new uncertainty at once. The ring was not static. Sagittarius A star flickers because the plasma near it changes on timescales of minutes. The array that made the image collected light over parts of days to build up enough signal, which meant the picture was a time average of a restless scene. The bright crescent shifted while the observation was underway, and what the reconstruction shows is a kind of mean pose of a dancer who never stands still. That raised questions about how to read the fine details. Does a brighter region mark a stable funnel of magnetic field where plasma orbits and sparks? Or is it the chance moment when a patch of turbulence flared during the exposure window? Another uncertainty came from the interstellar medium between us and the center. The same electrons that make the long radio filaments glow also scatter and blur radio waves on their way to us. Over many years, clever modeling of that scattering has allowed astronomers to peel back much of the blur, but the peeling leaves behind small residual uncertainties in the true sharpness and exact shape of the ring. Those uncertainties are now part of the canvas on which theory must paint. The mass is fixed well enough, but the spin is not yet nailed down. The ring's diameter is only weakly sensitive to spin, while the brightness pattern and the polarization structure carry more telltale clues. Polarization maps on horizon scales which trace how the magnetic field wraps and twists near the edge of the abyss have begun to appear. They show patterns consistent with a magnetized flow that is neither purely ordered nor purely chaotic a geometry, where stress sometimes builds in loops that reconnect and sometimes stretches into funnels that feed or launch plasma. These maps hint that the spin axis of the whole may tilt slightly relative to the disk of nearby orbits, but do not seal the case. Models now propose families of flows. In one, the inner region is threaded by a strong magnetic field that chokes and regulates the inflow, a state in which magnetic pressure becomes as important as gas pressure, and where jets can form even if they are faint in this quiet system. In another, the field is weaker, and turbulence does more of the mixing the inflow, settling into a thicker, puffier structure that radiates little because the energy it gains falls inward with the particles rather than turning into light. Both families can produce rings with the right size and a crescent with about the right brightness contrast, especially when time variability and scattering are accounted for. Disentangling them demands movies rather than snapshots, and that is where the next steps lead. The signature is also chemical and spectral. At wavelengths a little longer and a little shorter than the ring's main glow, the spectrum's shape points to how electrons are energized. Is the high-energy tail a broad thermal distribution stirred by many small shocks, or is it a non-thermal extension created in rare but powerful reconnection sites? The answer alters the predicted brightness at millimeter and sub-millimeter bands, and in turn, it changes how the ring should look at slightly different wavelengths. Comparing images across bands could therefore separate models that otherwise look similar in the average. The signature is also dynamical. If a luminous knot orbits close to the last stable path light from that knot, will be modulated by relativistic beaming and by gravitational lensing, and the modulation will have a preferred timescale tied to mass and spin. The fast variability recorded in high-energy flares already suggests timescales of tens of minutes, but a direct detection of a periodic component in the ring's light would be a stronger fingerprint. That search is underway through closure phase tracking that is sensitive to small shifts in the brightness pattern, even when the absolute image is hard to reconstruct in real time. The black hole signature reaches outward too. The narrow ring of darkness constrains alternatives to a true horizon. If a surface lay just outside the point of no return, light reflecting from it would fill in the interior and alter the brightness of the ring. If exotic physics replaced the whole with something that only mimics its gravity. From afar, the precise ratio of ring size to mass inferred from stars could shift. Thus far, the measurements agree with the simplest version of a spinning black hole in general relativity, leaving less room for exotic options, though not eliminating them entirely. The same comparison also limits how much dark matter can clump on the smallest scales at the very center, because any dense compact envelope would pull on the stars and change the ring size. In this way, a picture only a few tens of microarc seconds across becomes a lever for questions about matter that pervades the galaxy. Perhaps the most unsettling lesson of the signature is its calm. The mass is huge, the field is strong, the plasma is hot, the motions are near the speed of light, and yet the overall glow is faint compared to what it might be if the inflow were richer. The shadow is steady even as the crescent flickers. That calm forces a re-examination of how gas moves from the circumnuclear ring to the last orbits. Somewhere the flow is strangled or diverted. Somewhere the magnetic topology stores energy without letting it radiate. Somewhere the appetite of gravity is moderated by the starvation of supply. The horizon-scale image does not solve the riddle of faintness, but it pins the boundary conditions at the place where any explanation must end. In the years to come, the array will add more stations and more frequencies, sharpening the ring and tracing its polarization in time. Coordinated campaigns will catch a flare while the array is watching, tying a sudden high-energy flash to a brightening in one quadrant of the ring. Together with continued tracking of stars just outside, these efforts will turn a still frame into a chronicle. The black hole signature, once a hypothesis written in equations, is now a shape in the sky. It is the dark heart surrounded by a bright, thin echo of its own bending of space and time, a sign both definitive and provocative. It confirms the nature of the central mass, and in the same breath reminds us how much structure and history are hidden in the dimness that surrounds it. How many paths lead inward, and how many choices the plasma makes before it crosses the line from where light can return to where it cannot. The strangest feature of the galaxy's center is not its violence, but its restraint. A black hole of almost 4 million solar masses sits at the focus of the stellar ballet, and yet shines feebly many orders of magnitude below the luminous ceiling set by the Eddington limit. The inflow clearly exists for gas and dust stream inward through bars and rings and stars close to the center shed winds that load the environment with matter. Somewhere between the crowded inner parsecs and the last stable orbits that matter loses its brightness, its momentum, or both. Theories gather under a single phrase, radiatively inefficient accretion flow, which is a careful way of saying that energy goes missing from the light we can see because it stays trapped in the particles that carry it into the hole or is carried away by winds before it can be converted into radiation. In this picture, the plasma near the center separates into two temperatures. Heavy ions swallow most of the heat, while the lighter electrons that actually radiate receive only a fraction. The two species share energy by collisions too slowly for the electrons to catch up, especially in a thin, hot, rarefied medium where coupling is weak. The result is a flow that is bright in principle, but quiet in practice, a furnace that keeps its warmth in the coals instead of in the flame. Observations agree in broad strokes. The radio and millimeter spectrum lifts into a smooth bump that reaches towards sub-millimeter bands, while higher energies show only a whisper except during flares. Polarized light in the sub-millimeter range tells that the plasma is magnetized and that the Faraday rotation along the line of sight is modest, which in turn limits how much mass actually crosses the inner region. Those limits come in lower than what a simple capture estimate from the surrounding hot gas would suggest. At the radius where the black hole's gravity balances the thermal motion of the ambient medium, a sphere of influence the size of a fraction of a parsec one can define a notional inflow rate for gas in a hot bath. If that rate truly reached the horizon, the center would glow far more brightly than it does. Therefore, something removes most of the mass on the way in. Winds are the quiet thieves. In a magnetized, turbulent flow that is thicker than a cool disk, angular momentum can be transported not only inward by friction-like stresses, but also outward by magnetic tension that connects distant parts of the flow. When energy released by gravity gets trapped in the ions, it puffs the plasma up and seeds buoyant motions. Those motions open channels for gas to peel away in broad breezes. The flow thus becomes a fountain whose base leans inward, but whose sides lean outward, and the further inward one looks, the smaller the actual mass that remains to be swallowed. This picture matches the way the spectrum softens and the way the rotation measure stays small, and it offers a natural reason for faintness without asking the environment to be empty. Yet this is not the only path to quiet. Angular momentum itself is a gatekeeper. Gas that drifts inward from the circumnuclear ring does not fall straight down a chute. It must surrender spin at each step. Shocks, wave torques, magnetic stresses, and turbulence work together to drain that spin, but their cooperation is imperfect and episodic. The result is a stuttering supply. On many days the flow starves before it deepens, and the black hole waits behind a door that is mostly closed. On a few days, a door inside the inner parsec opens, and a fresh tongue of gas spirals inward far enough to graze the region that lights in millimeter waves. Those arrivals may seed the flares seen in high-energy light and in the near-infrared short bursts that do little to the long-term energy budget, but speak loudly about the shape of the inner machine. The quiet riddle includes a geometric tension. Some models arrange the inner plasma into a magnetically arrested state in which the field grows so strong near the hole that it chokes. The inflow regulates it in pulses and can even launch weak jets. Other models keep the field modest and let turbulence run the show. The polarization pattern on event horizon scales hints at ordered loops and at funnels, but the time averaging required to form present images smears the difference between a choked and a puffed flow. That is why repeated observations at several wavelengths taken while the brightness rises and falls are essential. If a flare correlates with a twist in polarization angle, a surge in sub-millimeter brightness, and a later dip at longer millimeter wavelengths, the sequence would favor reconnection in a magnetically dominated pocket that briefly heats electrons before cooling and thickening. If instead the flare arrives with slow, broad changes and no crisp polarization, swing turbulence may be the chief sculptor. The source of fuel also refuses to be simple. The winds of massive stars supply hot, fast streams. Cold clumps in the circumnuclear ring feed intermittent drizzles. Tiny, dusty objects on eccentric orbits wander through and are tidally stretched. Years ago, a small gas cloud on a plunging path was expected to trigger a banquet, yet the response was modest, perhaps because the cloud was stripped into mist well before it reached the last orbits, perhaps because the inner flow simply vented the extra heat in broader winds. This episode underlined an important lesson. The rate at which material enters the sphere of influence does not set the rate at which it reaches the horizon. Between those two scales, the plasma is a sieve, and the holes in that sieve widen whenever magnetic loops inflate. The electrons that do radiate draw their energy from several taps. Weak shocks add heat broadly. Magnetic reconnection in braided fields injects small populations of fast particles with power law tails. Turbulent cascades move energy from large eddies to smaller ones where it can be absorbed. Each channel leaves a signature. Shock heating tends to build a smooth, near-thermal distribution of electrons and a steady sub-millimeter glow. Reconnection prefers sudden localized events that boost a small fraction of electrons and light the high-energy bands. Turbulence supplies a restless baseline upon which the other two write their lines. The observed mixture of a steady dim glow punctuated by irregular flares points to all three channels at work, the exact blend changing with time as the field rethreads itself. The riddle reaches beyond physics, inside the last light ring, and out into the wider circumnuclear environment. Young clusters carve bubbles whose hot interiors press on the inflow. Large-scale magnetic filaments stiffen paths and damp shear. Outflows above and below the plane transport angular momentum away, and even if they are faint in light, they can be loud in dynamics. Every such influence pushes the inflow closer to the regime where most mass is lost before crossing the horizon. In that sense, the faintness is not a failure to feed the black hole, but a success of feedback that prevents a runaway. The quiet is therefore not emptiness, it is balance. What will break the riddle is time-resolved mapping. Polarization movies at millimeter and sub-millimeter wavelengths can track how field lines twist during a flare. High-resolution radio images at slightly different frequencies can sample electron energies across the flow. Sensitive X-ray timing can chase the shortest cooling times and reveal whether fast electrons are constantly replenished or made only in bursts. Infrared spectroscopy can watch emission lines change in width and shift marking where streams thicken or thin. Finally, a patient census of rotation measure season by season can diagnose whether the inner mass flow is rising or falling on the slow clock of the circumnuclear ring. When these threads are woven together, they may show that the central engine is not broken, but finely tuned to stay dim. Most of the time, a hearth where fuel smoulders, heat hides in ions and winds, lift away the excess before it can blaze. The galaxy's heart then reads as a teacher of moderation, heavy hot and magnetized yet disciplined, speaking in occasional sparks, rather than in a continuous roar, leaving space for structures to approach without being destroyed, and for the next chapter to assemble just outside the horizon's patient edge. The inner few tens of parsecs are strewn with fossils of past fire, and each fragment carries a memory of pressure shock and gravity. The most conspicuous scar is a wide shell of hot gas offset from the exact center, a supernova remnant whose bowing edge presses into surrounding clouds and leaves filaments glowing in radio light and in lines from shocked atoms. Its curves and knots speak of an explosion that tore through a medium already roughened by winds and magnetic tension, so that the blast became lopsided and its energy poured preferentially where the path was softest. Wrapping and overlapping this shell are smaller remnants, some so faded that only X-rays betray their heat, others fresh enough that molecular species which form only in hard shocks enrich the local chemistry. These relics were born from massive stars that once lit the circumnuclear rings, stars that lived briefly and died so thoroughly that their ashes still shape the flow. Their compact cores remain. Neutron stars with intense magnetic fields flicker in soft and hard light, some as magnetars that occasionally shrug and send short bursts through the region, others as quieter pulsars whose beams graze Earth and mark their spins with millisecond precision. Near the center, such objects are both common and hard to see, screened by dust and by the confusion of sources, yet their signatures leak through and add a persistent whisper of high-energy photons to the spectrum. The same star deaths that left neutron stars also left a smaller, darker population of stellar mass black holes. They drift in the nuclear star cluster, and then gradually sink inward through the slow tug of dynamical friction, building a swarm whose orbits are tight and whose interactions are frequent. When one of these black holes captures a companion star, or skims gas, or brushes a dense clump, it can light as a transient in X-rays, a brief flare that marks the moment when hidden mass meets accessible fuel. Some pairs spiral together and merge, releasing energy in gravitational waves that ripple outward, inaudible to current ears at the center's distances, but destined to be heard by future detectors that can listen to long, slow tones. This inward drift of heavy remnants carves a shape into the central density profile, a dark cusp that theory expects and observation seeks, and it changes the stories that play out in the inner parsec by turning encounters into a frequent script. Collisions and near misses among stars, compact cores and cold clumps leave heat and light, and sometimes shredded streams. There are hints that some of the unusually luminous red and dusty sources that wander near the black hole are not simple clouds, but the swollen debris of stars bloated by repeated tidal brushes or binaries swaddled in shells after close passages that stirred their orbits and their atmospheres. Elsewhere, tight groups of young, massive stars massed into clusters suggest that infall and starbirth happened in bursts. One cluster sits like a recent ember, its winds carving bubbles and its radiation gouging cavities in the surrounding medium. Another lies farther out, older and more dispersed, its most massive members already dead, its remnants now part of the growing dark tide. These clusters may have formed in place, or may be the battered cores of stellar systems that spiraled inward from farther in the disk, their outer stars stripped by tides, until only a dense heart remained to reach the bulge where it unraveled and fed the nuclear cluster. If such inspirals repeated over long periods, the center would layer itself with the rubble of many small galaxies within the galaxy, a palimpsest where each line of stars and remnants writes over the last. Supernovae have left more than shells. They have etched chemical notes into clouds. Ratios of elements in cold gas reveal overabundances that betray repeated core collapse explosions, and those enrichments seed the next generation of stars with heavier atoms that cool gas efficiently, but also alter the way dust forms and charges. In filaments that curve along the bar, silicon monoxide spikes where shocks have ground dust to sand and released silicon into the flow, while the molecules that cling to grains in quiet places reappear after calm returns. This chemical weathering makes the relics into teachers of physics, because the molecular map records where energy was deposited and where it diffused. The echoes of brighter days appear on scales larger than any single remnant. Above and below the plane balloon, two giant lobes filled with hot plasma and threaded by soft light that hints at particles driven outward long ago. Their smooth surfaces and broad symmetry suggest an outflow that was sustained for a long interval rather than a single blast, perhaps a starburst in the nuclear ring, perhaps a more direct breath from the black hole. Closer to the plane, fluorescent lines in distant molecular clouds brighten and fade with delays that match light travel times from the center, as if the clouds were mirrors lit by X-ray candles that burned centuries ago. These remote reflections imply that the central engine once flared far more powerfully than it does today, leaving the present quiet as an interlude between episodes. The relics of that history are not limited to gas. The orbits of certain fast stars hint that stellar families were once more crowded, and that dynamical exchange swapped partners and ejected some members. Hypervelocity stars that now sail in the halo carry a message for those who can read their directions and ages as they point back to kicks near the central black hole, where a binary split one star bound to a new tighter path and the other flung outward at extraordinary speed. In the opposite direction of extreme, some faint dwarfs may have been fed to the center hole, their cores spilling stars and compact remnants into the nuclear cluster, their gas shocking and then cooling into new clouds. The inner parsecs thus become a marketplace of material where every coin is spent twice, once as a shell or a wind, and again as a seed for the next structures. Among the most tantalizing possible relics are black holes heavier than stellar and lighter than supermassive, the intermediate class that theories allow and hints tempt. A few compact radio sources move as if they were bound to dark masses, and a handful of unusual X-ray transients flare with luminosities and timescales that fit the idea of a heavier, quieter ether. If such bodies dwell in the inner bulge, they would stir their neighborhood's heat nearby gas and alter the apparent shapes and speeds of stars that pass near them. Their existence would also fill a gap in the story of how central black holes grow, offering stepping stones between small deaths and the great weight at the core. Even if they are rare, their influence would be lopsided for a single encounter, with one could tip a star into a loss cone that leads to tidal disruption at the central black hole, which would bloom as a bright event and then fade, adding a single loud note to a long, quiet song. The cumulative effect of all these relics and remnants is to crowd the inner region with overlapping stories. A neutron star's burst briefly ionizes the skin of a nearby cloud, which changes how that skin couples to the magnetic field, which deflects a thin stream that would otherwise have edged closer to the heart. A supernova remnant's pressure corrals cold gas into a straight ridge that a magnetic filament later binds, which becomes a conveyor for a slow drift of material into the circumnuclear ring. The weak wind from a relic cluster keeps a channel open above the plane, along which future outflow can climb, shaping the future path of energy away from the disk. Nothing here is isolated. Every fossil leans on every fresh structure, and the entire scene is a layered archive where present motions are guided by past blows. Reading the archive will require patience and a taste for coincidences that are not coincidences. High-resolution maps that compare element ratios to shock tracers, catalogues of compact sources cross-matched across radio-infrared and X-ray bands, long-term timing of magnetar bursts, and of slow changes in fluorescent cloud lines, all of these will stitch the relics into a history. The prize is not only a backward glance, it is a forecast, because the density of compact remnants and the scars of old shocks set the probability that the next bright event will be a tidal disruption, a starburst ringlet, a minor jet, or a simple hush. In a sense, the center is a museum where the exhibits keep talking, where the displays push on the walls, where every broken piece is also an engineer of what comes next. The crowded stories overlap and blur origins, but they also reveal a continuity. Matter is burned, rearranged, cooled, and burned again, and the gallery of remnants is the memory that guides the hand that writes the next line near the horizon. In a region where randomness seems to reign, scattered hints begin to line up as if time itself were a quiet architect. The first clues come from far clouds that do not live near the black hole at all, but many tens to hundreds of light years away, clouds so dense that starlight struggles to cross them. Yet they glow in a narrow line from neutral iron at about 6 4/10. Kilo-electron volts a signature that is easiest to excite with hard X-rays. Those clouds brighten and dim over years to decades, and the changes sweep across their faces like ripples, not everywhere at once, but in fronts that move at the speed of light projected along the depth of the region. When mapped carefully, the apparent waves point back toward the center, as if the clouds were giant mirrors catching lighthouses that flashed in past centuries. The timing does not match the feeble modern flares that rise and fall within an hour. It matches beacons' orders of magnitude brighter, lasting longer, the kind that would have thrown enough hard light to awaken distant iron out of its calm. Whether those beacons were single eruptions or a rain of bursts remains open, but the pattern of echoes is itself a clock. It lets watchers reconstruct a timeline that the direct line of sight denied. Meanwhile, closer in spectra of the circumnuclear gas change with seasons and years. Lines that trace ionized atoms wax and wane, their widths and centers shifting as if the average temperature and bulk velocities sway in response to a variable driver. In some epochs, The near-infrared glow rises with small, hard X-ray events and is followed by a dip at millimeter wavelengths. Hours later, a sequence repeated just often enough to look like more than chance. In other epochs, the order reverses, or one of the steps is missing, as if a second mechanism sometimes takes the lead. These coincidences in time begin as curiosities and end as constraints. Any model that explains the central machine must pass through the same order of acts, at the same moments that the sky records. Even the chemistry seems to keep time. Molecules in clouds along expected light echo paths change their ratios in ways that hint at sharper ionization fields in the past. Species that cling to dust in quiet conditions appear depleted and then return, a cycle that could mark the passage of a hard radiation front that baked ice mantles away and left them to rebuild slowly. Farther out in the giant lobes above and below the plane, diffuse light, at certain energies, fades unevenly, and the rate of fading suggests that the particles which make that glow were energized not in the distant past, but within the past few million years, perhaps much more recently for some zones, and the asymmetry in their decline hints that the faucet in the center did not open and close smoothly. The coincidence that curls these facts together is the schedule of inflow. As bars and rings pass mass inward in fits, as clusters erupt and then grow quiet, the rate at which material reaches the inner fraction of a parsec must wobble. When the flow thickens and magnetic loops knot, reconnection flares repeatedly until the topology changes and the activity relaxes. In that picture, the archive of ion echoes would be the long record of a previous period when the inner flow held a geometry that encouraged powerful repeated bursts, perhaps because field lines were trapped and forced to rearrange in tight cycles, perhaps because a small jet existed briefly and its hard light bounced far. The present period, by contrast, appears to be a low state in which the same mechanisms still run, but with smaller fuel packets and lower field tension, so that we see only small flares and a steady murmur. The fact that the far clouds still shine in delayed light, even as the center stays mostly calm today, is not a contradiction. It is a gift of geometry, a way for the past to remain visible while the present hides. Time-linked coincidences also appear in the paths of stars. Over roughly 2 decades, the closest known fast star swung through pericenter, and the timing of tiny changes in its spectral lines matched the gravitational redshift expected in a curved spacetime. At nearly the same epoch, a series of bright near-infrared flares turned up within months of each other, then hushed. Causal ties are not claimed. The distances and mechanisms differ. Yet seen together, the paired timings whisper a broader lesson the center's many subsystems can speak at once, and when they do, the overlapping voices write a chorus that a patient ear can separate. The practical use of such coincidences is powerful. If a future hard X-ray mission sees the iron reflections in a given cloud rise again, and at the same time an increase in near-infrared flares is caught, and at the same time sub-millimeter polarization angles begin to wander faster, the aligned timing would be a strong indictment of a reorganizing inner flow. That forecast is not only wishful, it is a working strategy behind long campaigns that enlist observatories across the spectrum to sit on the center for weeks and months. The hope is to catch a flare, while the array that images the horizon is also collecting, while infrared polarimeters are also watching, while radio arrays are also tracing the filaments, so that one episode can be stitched into a movie with a single clock. Even mismatches are instructive. There have been seasons when clouds have shown no change in reflected lines, despite upticks in local flaring, suggesting that the hardest photons were either trapped or beamed differently, or that the geometry hidden from us directed them away from the particular mirrors we can measure. There have been years when the rate of near-infrared flares rose, tempting reports of long-term brightening, only for the rate to fall again, as if the process has memory and acts with a mean that we have not watched long enough to measure well. One cannot help suspecting that a slow oscillation may be riding the faster weather, a cycle tied to how the circumnuclear ring rearranges itself, how mass piles at preferred longitudes and then spills over into the inner streams. If that slow driver has a period of decades, then the iron echoes a few hundred light years out are the only way we will glimpse its peaks until enough human time passes. In some nights the coincidences sharpen to single minutes. A near-infrared flare with a strong rotation of polarization angle arrives, and within the same hour a soft X-ray flare peaks, and within a few more hours the sub-millimeter flux dips as if the inner pocket that was heated became briefly opaque before relaxing. If that sequence repeats enough, it will become a diagnostic. Even now, the handful of cases suggests an order acceleration of electrons emission in near-infrared upscattering or direct synchrotron at higher energies expansion and thickening at longer wavelengths. The beauty of this order is not only that it fits plausible physics, but that it gives watchers a timer, the delay between steps, measures, sizes, speeds, densities, and field strengths that no static image can reveal. Time then turns from nuisance to microscope. The remaining danger in reading coincidences is confirmation bias, the human tendency to trace patterns through noise. The antidote is to let time guard against itself, to demand that a sequence repeat in multiple seasons, to insist that independent instruments confirm steps to use blind forecasts rather than retrospective fits, and to treat non-coincidences as equally valuable. When the iron echoes do not change in step with local flares that speaks about beaming and absorption, when a predicted sub-millimeter dip fails to follow an infrared flare that speaks about the geometry of the emitting region or about a flare made by a different mechanism. In this way, the record of years becomes a ledger in which every aligned column and every empty one sharpens the story. What began as a set of suspicious alignments between unrelated phenomena matures into a coherent chronicle in which energy injections, propagation through fields and flows, and delayed reflections in far mirrors all share a single axis time. The heart of the galaxy thus reveals itself not only through images or spectra, but through schedules, through the choreography of light that crosses different bands at different moments, and the shadows that light throws on distant clouds long after the dance seems over. The coincidences are not coincidences at all. They are the distorted yet faithful echo of a central rhythm that sometimes beats loudly and sometimes barely at all, but always leaves its trace in how the sky brightens, dims, and brightens again right on time. The center is a laboratory where equations meet their limits, and the instruments are the stars themselves. They sweep out clean arcs that look simple until a closer look reveals the small hesitations and nudges that only curved space-time can give. When a fast star dives toward its closest approach, its light stretches to longer wavelengths, not because dust intervenes, but because time itself runs differently in the deep potential. The measured shift matches the prediction of general relativity within the uncertainties of the measurements. Then, as years pass, and the same star returns to that tight turn, the ellipse it traces has rotated a little, the point of closest approach slipping forward, an advance of the periapse that Newton's law alone cannot supply. Together, these two signatures make the first lines in a ledger that tests gravity not in the weak field of planets, but in the strong field near a supermassive weight. Yet the ledger is far from finished. The orbits of many stars carry small irregularities that at first glance could be blamed on deviations from general relativity, but the inner region is not empty and the stars do not move alone. A fog of unseen mass surrounds the black hole, a mix of stellar remnants, low-mass stars too faint to track, and possibly a smoother distribution of dark matter that rises toward the core. That extended mass would tug on the fast stars and add a retrograde precession that partly cancels the relativistic advance, while close encounters with compact objects would scatter velocities in ways that mimic or mask gentle drifts. To subtract these astrophysical confounders is to peel an onion whose layers each smell of gravity but different kinds of gravity. The very effort becomes another test because the amount and distribution of the extended mass can be bounded by how much deviation from a clean, relativistic precession the data allow. So far the allowed envelope is slim. There is room for a mild cusp of dark objects, but not for a dense spike that some theories predict if dark matter could compress adiabatically as baryons fell inward. There is room for stellar mass black holes to concentrate, but not so many that they would erase the forward creep of periapses altogether. In this way, a few arc-seconds worth of stellar arcs become a tool to weigh matter that neither emits nor reflects light. Modified gravity proposals take their turn under the same gaze. If the inverse square law were altered at parsec or sub-parsec scales, if a fifth force rode alongside the familiar four, or if the central object were not exactly the solution described by general relativity, but a cousin in a broader family, careful tracking of orbits would show patterns that no amount of unseen mass could fake. Some theories predict changes in how precession scales with the size and eccentricity of orbits. Others predict small deviations in the relation between gravitational redshift and orbital speed at closest approach. The data so far do not demand any of these additions. They sit comfortably inside general relativity, but they do so with uncertainties that still leave seams showing places where a small tilt could hide. That is why observers chase the discovery of a pulsar in a tight orbit about the black hole. A neutron star that beams radio pulses with clock-like regularity would turn the center into a precision timing experiment. The delay that a pulse suffers as it passes through curved spacetime, the extra time spent near pericenter. The way the plane of the orbit precesses from frame dragging caused by the spin of the black hole. The imprint of the quadrupole moment that reveals whether the central object's shape matches the exact proportion that general relativity requires for a spinning hole. All of these would become measurable, not as hints, but as crisp numbers. Even the equivalence principle could be tested in the strong field by comparing how different species of matter in the same potential fall and precess. The search continues through scattering interstellar electrons and through crowds of confusing sources, because the reward would be an exquisite scale set just meters from the horizon for every microsecond of recorded time. Frame dragging itself remains a tantalizing goal. The spin of the black hole should twist spacetime around it, and orbits very close in should feel that twist as the line of nodes slowly turns. For stars at present distances, the effect is small and entangled with all the other tugs. But as measurements improve, and as shorter period stars are found, the hope is to see that slow torque directly and to translate it into a spin that can be compared with the value hinted at by horizon-scale images and by polarization patterns. The comparison would reach across instruments and methods, asking whether a single angular momentum accounts for both the dynamical dance just outside the last stable orbits and the brightness pattern on the ring that gravity bends into a circle. If the two disagree, then something in the story is missing. Either the fields and flows near the hole complicate the light beyond expectation, or an unmodeled mass distribution nudges the stars more than believed, or gravity's law needs an amendment. The same orbits can speak for or against a dense cluster of low-mass black holes, or of hypothetical scalar field condensates. If many compact bodies haunt the inner parsec, a fast star's path will suffer a slow random walk in energy and angular momentum, a resonant relaxation that broadens the distribution of orbital elements over time. A scalar field could add a smoother tug that shifts precession in a way that increases with the fraction of the orbit spent far from pericenter. By comparing multiple stars with different shapes of orbit, by watching changes accumulate over decades, and by using stellar spectroscopy to lock down line-of-sight velocities with meter-per-second ambition, astronomers can begin to separate a granular tug from a smooth one, a local kick from a global pull. Beyond stars, hot gas offers its own clocks. The rise and fall of flares with suggestive timescales of tens of minutes, if tied to orbital motion near the last stable paths, become probes of the gravitational potential where it bends light the most. Polarization swings attached to those clocks could measure how light paths wrap around the hole before they reach us, a lensing that depends on spin and on any deviation from the precise metric that general relativity writes. Again, astrophysics complicates the reading because the flares may be made by reconnection or by turbulence rather than by tidy hotspots, yet even messy phenomena cannot avoid the rules of the well, and those rules leave temporal fingerprints. All of these tests demand patience and clean modelling, but they also benefit when the sky is uncooperative. A close passage between a star and a compact remnant, a sudden burst that blows a pocket of gas into a new shape, or a temporary surge in inflow that shuffles magnetic geometry. Each event is a small experiment that pushes the system off balance and reveals restoring forces that steady it. The response times and the ways the various tracers drift back toward their long-term means are themselves measures of how gravity and pressure and field tension share authority. In the end, the center keeps passing every exam that we have written with the standard book open to general relativity. Yet the margins of those pages are full of notes that say watch here and watch longer and add one more instrument. The equations hold, but the edges fray, because the classroom is not a vacuum. It is a crowded, noisy, beautiful hall, where unseen matter whispers from the wings, where compact remnants slip between seats, where magnetic lines drape over desks, and where the teacher gravity speaks with a clear voice that we can hear even through the murmur. The promise is that with more time and better timing, with sharper pictures and steadier clocks, the seams will close, or else they will open in a way that no amount of modelling can hide, and then the heart of the galaxy will either confirm its perfect obedience to the current law, or announce a gentle deviation that sends the law back to committee for revision. The last steps before the point of no return are a world built of curves, where space bows and time stretches and light itself is forced to thread a maze whose walls are made by gravity. The plasma here does not drift. It orbits on paths that are almost but not quite circles, their stability tested by tides that never rest. Just outside the last stable orbit, matter piles into a narrowing band where centrifugal balance and gravitational pull negotiate through pressure and magnetic stress. In this band, electrons and ions share space, but not always temperature, with heavy particles carrying most of the heat, while lighter radiators glow in brief bursts when shocks and reconnection deliver energy across the gap. The magnetic field that pervades the inner flow is neither random nor fully ordered. It is braided by shear and bent by infall into loops and funnels, and it stores energy like a spring. When two loops of opposite direction are pushed together by turbulence or by the slow winding of the flow, they snap and rejoin in magnetic reconnection layers that release energy into particles and into waves. Those waves run along the field at the Alfvén speed, pushing disturbances outward and inward, occasionally shaking the funnel that points along the spin axis of the black hole. Even when no obvious jet is present, this funnel guides plasma into narrow streams and shapes how heat and angular momentum escape. Where the field becomes strong enough to rival the pressure of the gas, it can choke the flow and set up a magnetically arrested configuration, a state that throttles the inward drift impulses and prepares the stage for short, bright events. The geometry maps into light through several lenses at once. Electrons that spiral around field lines emit synchrotron radiation that is naturally polarized, and the direction of that polarization rotates as the field twists with height and radius. General relativity then adds its own twist. The polarization vector is parallel, transported along a path that bends and wraps so that a given patch of plasma can send us light whose electric field appears to turn as a function of angle and time even when the local field is steady. Close to the hole, light does not go straight. Photons that start inward at shallow angles skim around the abyss and return with delays set by their tight loops. A face of the disk that would be hidden in a Newtonian world becomes partially visible as gravity bends its light up and over the rim. A compact knot of hot plasma that rides the last stable orbit therefore does not merely brighten and dim because of Doppler boosting as it approaches and recedes. It also paints a moving crescent on the sky, whose brighter side is further brightened by lensing, whose darker side is partly filled by light that has swung behind the hole and back, and whose phase is shifted by the slowing of time in the well. The result is a light curve that carries beats tied to orbital periods, polarization swings tied to field geometry, and small echoes tied to the extra laps of bent photons. When observers integrate for long enough to amass signal, those swift dances blur into the lopsided ring captured by the planet-sized array of radio dishes called the Event Horizon Telescope, a ring whose diameter anchors the mass while its bright arc hints at flow direction and spin even as the specifics are softened by averaging. In faster glimpses, at shorter wavelengths, the dance hints through flares and rapid polarization changes that sometimes align with the orbital timescales expected a few radii above the horizon, as if small knots of accelerated electrons were indeed circling and cooling in view. The plasma has its own weather. Shear drives, turbulence, amplifies fields, and amplified fields snap in bursts. In that process, a fraction of the particles climb to energies where they radiate quickly and then fall back toward the thermal pool, a cycle that sets the short duty cycle of bright events. At the same time, radiation is trapped by the flow because scattering and absorption are rare in the thin medium. So heat rides inward with the ions rather than escaping as light. This is the secret of the dimness, and also the reason the inner region can change quickly when a pocket of energy finally couples to radiating electrons. The geometry of spin adds a slow tilt to the story. If the black hole turns, it drags space-time around with it, and circular orbits that are aligned with the spin have different last stable radii than those that oppose it. The difference alters orbital periods and shifts preferred locations for reconnection and brightening. A misalignment between the spin axis and the plane of the incoming flow can twist the inner disk, setting up a warped structure where precession modulates how we see the brightest regions. Such precession could imprint slow cycles on the statistics of flare phases and may also deflect the weak outflows that vent angular momentum, helping to create the chimney-like paths that carry energy above the plane into the giant lobes farther out. Every property is coupled. The rotation measure that tells how much the plane of polarization has twisted along our line of sight depends on electron densities and field strengths in the funnel and in the outer skin of the flow. The position angle of the bright crescent's polarization depends on field geometry near the horizon and on how light was bent on the way. The balance between a steady submillimeter glow and the number of near-infrared and X-ray flares depends on how often reconnection reaches into electron energy distributions rather than warming ions alone. Even the relative timing between a near-infrared spark and a shallow dip at longer millimeter wavelengths can be read as a chronometer for expansion and cooling in a parcel that briefly turned optically thick. All of these are clocks and compasses that point toward the horizon in different units, and the plan is to use them together to make time-resolved polarimetric imaging across neighboring bands and to coordinate those images with fast spectrophotometry that can write down the order of events when the inner flow speaks. The goal is a movie of fields and light in a place where none of the ordinary rules of straight lines apply. As the horizon is approached, the very definition of location becomes slippery. A photon can circle the hole several times before escaping, so the apparent position of a flare on the ring is a blend of where it was made and of how its path was braided. A field line can thread the horizon and still guide plasma outside it, so the frame in which energy is stored has both an inside and an outside aspect. Infalling matter never quite reaches the horizon in our time, but does so in its own clock, which makes the last stage both sudden and smeared, depending on the frame of thought. The physics of dissipation is no longer a question of collisions alone, but of collective behavior in a collisionless plasma, where instabilities grow and saturate, where pressure can be anisotropic, and where heat fluxes can run along field lines rather than spreading evenly. These details, once esoteric, become decisive in deciding whether the inner edge puffs or thins, whether reconnection heats electrons effectively, and whether the funnel along the axis behaves like a nozzle or like a leaky sieve. The closer we read, the more a paradox emerges the horizon which permits no signals to escape from within, nonetheless shapes every signal we see from just outside by how it bends and delays light, and by how it fixes the last place where circular orbits can exist. That indirect speech is powerful enough to rule out many alternative objects that would reflect light or carry surfaces, because such surfaces would fill in the darkness and would trap radiation in ways that would leave a different spectrum. The remaining ambiguity lies not in whether the center holds a real black hole, but in exactly how that hole is fed and fenced by fields. As instruments sharpen the path forward is clear. Add stations and baselines to the array that images the horizon to turn, still frames into moving ones. Watch the polarization pattern at horizon scales change while near-infrared and X-ray fluxes rise. Measure rotation measures night by night while mapping the bright crescent's position angle. Search for periodicities in closure phases that would betray orbiting hotspots, and link those patterns to the timing of light echoes in distant clouds so that near and far can be tied to a single episode. The descent toward the horizon is not a fall into silence. It is an approach to a boundary that rewrites how motion and light behave. Breath slows because the scales at which these rules matter are smaller than we can readily imagine, and faster than our ordinary instruments can see. Yet with patient synchronization and with careful physics, the tilted space just above the line from which light cannot return begins to speak. It speaks in crescents that shift in vectors, that turn in echoes, that arrive late in small dips, that follow sparks in a choreography that is more than weather and less than a script. It is the real shape of the galaxy's heart in the language of fields and curves, and every step closer to the horizon turns another page in a book that gravity began when the first gas flowed inward, and that we are only now learning to read without flinching. Gather every thread from the outskirts to the horizon, and a living portrait forms not of a static machine, but of a breathing center, whose rhythms travel outward through rings, lanes, filaments, clouds, clusters, lobes, and finally into the halo where old stars drift with memories of kicks received long ago. The inner core is small in extent and vast in consequence. Within a few light years, gravity and magnetic pressure shape a maelstrom where cold clumps orbit in a perturbed ring, hot plasma swirls in a thickened flow, and lines of force tie sky to disk in a scaffold that resists and redirects motion. Across that scaffold reconnection, light's brief high-energy fires, turbulence stirs a constant low glow, and winds steal mass before it can fall. From slightly farther out, supernova scars and compact remnants inflect the pressure field and seed the next rounds of chemistry and star birth, while time-delayed mirrors in distant clouds replay historic outbursts in the language of iron. Close in a bright crescent surrounding a stubborn darkness registers mass and hints at spin, its lopsided glow whispering that the funnel of force near the axis is real, even if jets are only ghosts. The picture is coherent, a light-starved engine in a cluttered, magnetized city, whose roads all slope inward, but whose traffic is metered by gates that open and close without a fixed clock. That coherence does not end the questions. Why do the cold clumps in the circumnuclear ring so often ride past the last easy exit without tumbling inward? Do tides, fields, and feedback set a universal threshold for collapse and delivery? Or is their balance still a coincidence produced by the present distribution of mass and the current state of the bar? How many compact remnants crowd the inner parsec, and do their encounters inject enough random kicks to explain the spread in fast star orbits, the rare dusty wanderers, and the occasional hypervelocity exile? Are there intermediate mass black holes hiding among the compact sources? And if so, do they channel gas and stars into the last orbits, or act as roadblocks that stir and heat without feeding the heart? The faintness of the central glow raises more puzzles. If winds peel away most of the inflow, how does the funnel geometry store and release magnetic energy without turning the engine bright? If the electrons that radiate are cycled by reconnection and shocks, How much of their energy is shared with ions, and how much escapes as light, and does that partition change when the inner flow briefly organizes into a magnetically arrested state? Can we watch that organization happen in polarization movies that catch loops forming and breaking in rotation measures that spike and subside in closure phases that betray a knot sliding along a last orbit? The magnetic lattice offers both explanation and enigma. Its long filaments and arc crossings are clear in radio and submillimeter maps, yet the fuel that keeps their electrons bright must be renewed. Where exactly are the accelerators? Are crossings sites of persistent reconnection that both maintain the lattice and regulate inward motion? Or are they transient scars that migrate with the tides of inflow? Does the lattice's large-scale architecture connect to the giant lobes above and below the plane as a memory of past steady outflow? And if so, can we date those episodes by the fading of soft light and by the gradient of particle energies with height? The outer disk keeps delivering mass along arms and bar shocks, suggesting that the inflow is a principle rather than a phase. If this is true, then the center must cycle through long quiets and shorter louds, building free energy in fields and orbits, and then releasing it in bursts, whose echoes we read now as ion reflections. Do these cycles have a preferred period set by the bar pattern speed and by resonances in the inner disk, or are they chaotic, their durations the outcome of a turbulent competition between ring pileups, cluster feedback, and magnetic rearrangement? A single well-timed campaign could decide. Imagine the bright crescent imaged at 2 adjacent millimeter bands while near infrared polarimeters and fast X-ray timing ride along all, while a sensitive hard X-ray eye maps iron echoes in the nearer clouds. Catch one large episode with that ensemble, and the time order of peaks and dips of angle swings and centroid motions will cut the model space down to a few geometries rather than many. The inner core also touches questions that appear unrelated at first glance. The mass estimate from stellar orbits and the size of the black hole's shadow already leave less room for exotic central alternatives and for steep dark matter spikes. Can continued orbit tracking and horizon-scale imaging together constrain whether the distribution of unseen mass falls inward smoothly or clumps into a dark cusp of stellar remnants, and in doing so, teach how galaxies concentrate their leftovers? If a pulsar is found on a tight orbit, could its timing fold in tests of frame dragging and of the quadrupole moment that finally nails the spin? And by cross-checking with polarization maps on the ring, resolve the remaining degeneracy between geometry and dynamics? These are not idle hopes. They are roadmaps already drawn. Add baselines to the planet-sized array to sharpen the ring and to follow it in time. Build fast polarimeters that can measure rotation in the light vector during a flare without smearing the signal across minutes. Expand millimeter and submillimeter coverage to stitch the electron energy distribution and to catch optical depth changes as they happen. Keep deep radio surveys of the bulge to trace dim filaments as they brighten and fade and to watch knots migrate along wires. Keep precise spectroscopic and astrometric watch on fast stars, knowing that the next small advance of periaps or the next unexpected drift in a line of nodes will either tighten general relativity's bonds or loosen them. Meanwhile, continue to read the slower clock's rotation measures season by season, element ratios in clouds near light echo fronts, decade by decade, the ballooning or shrinking of hot lobes over generations. The portrait is living because it accepts contradiction as temporary. cold and hot coexist and convert order and turbulence, alternate gravity's simple pull and magnetism's elastic push trade lines in a duet that never resolves. The black hole's signature is both definitive and incomplete, a shadow that fixes mass while leaving spin and feeding geometry to inference. The outer inflow is a river with bends whose positions drift as the bar turns, as rings inflate or deflate, and as clusters blow and then fall quiet. The lattice is a frame that sometimes stiffens and sometimes yields. In such a system, questions are not irritants, they are instruments. Each unanswered one points to a measurement that can be made to a movie, that can be filmed to a spectral line, that can be tracked as it brightens, fades and brightens again. The inner core therefore becomes both subject and guide. It tells us that the right scale for discovery is not a single instrument's strength, but the overlap of many, that the correct clock is not one cadence, but several nested, and that the most faithful path to understanding a quiet engine is to listen in many languages at once. Beyond the details lies the larger, unfinished thought. The center does not dominate the galaxy's light, yet it rules the galaxy's story by setting a boundary condition for what gas can do when gravity has its fullest say. If the present epoch is a hush between songs, then the echoes on far clouds and the faint lobes above the plain are the memory of verses already sung, and the scattered flares are the clearing of a throat before the next line. What next observations may reveal is less a single secret than a grammar, how inflow writes a sentence where punctuation falls in pauses that look like rings, how magnetic clauses tie subjects to objects along straight filaments, how the verb of reconnection turns a stored thought into a bright exclamation. The silence that lingers now is not emptiness. It is the depth of a breath drawn before speech, the held moment in which the heart beats behind unanswered doors, ready to answer the next knock with a burst of light.